Today we're going to be considering a theorem about the dimensions of spaces and subspaces, and then moving on to some standard bases for any vector space. Let's start with the theorem. Theorem 1.8 reads, if V is a finite dimensional vector space over a field F, and W is a subset of V and is a subspace, then W and the quotient space V quotiented against W are both finite dimensional vector spaces, and the dimension of V is equal to the dimension of W plus the dimension of V quotient against W. This is a very useful theorem, and you can do some modifications on it to get one of the most famous linear algebra theorems, namely the Rank-Nullity theorem. For now, let's proceed with the proof, which says if W is a subspace of V, and if W1 up to Wm is a basis for W, then there's a basis for V of the form W1 up to Wn, V1 up to Vn, for some vectors V1 to Vn in V. Indeed, if W is a subspace of V, but W does not equal V, then there's at least one vector, V1, which is in V except for W. That is, we're just trying to think about a basis for W and then extending it to a basis for V. We then note if W does not equal V, then there's at least one vector, V1, and the set of vectors W appended with V1 are linearly independent. If these vectors do not fully span V, then the argument can be repeated, providing a vector V2 such that the vectors W1 up to Wm plus V1 and V2 are still linearly independent, and you can continue this until you must terminate. The reason you must terminate is by the basis theorem, which shows that this process finally stops. Because, since V is finite dimensional, it has a basis of m plus n vectors for some n, so there can be no more than m plus n linearly independent vectors in V. That is, you cannot have more linearly independent vectors in a space than there are dimensions of that space. You can also do this argument starting from the empty set to give a basis for any subspace of V. We then will consider the quotient space and note that vectors in the quotient space V quotiented against W are equivalence classes V plus W for vectors V and V, and we'll note that since Wi plus W is equal to W, that is, choosing any element in the subspace, particularly the basis elements of the subspace, and adding them into the subspace will just give you the subspace itself. It follows that these equivalence classes for I from 1 to n span all of V quotient against W. That is, we consider all those elements that we've generated previously, and we see that they must span V quotient against W. We'll note that if we have a linear combination of these equivalence class vectors, namely Vi plus W, if you have a linear combination of them, then, and if that linear combination is equal to W for some coefficients, then the sum of the original vectors must be in W. That is because you simply distribute over the coefficient AI. And once you distribute the coefficient AI into W, that's clearly in W. So if this is equal to W, then these remaining elements must be in W. Therefore, we get that the sum from 1 to n of these is in W, so we can rewrite them as a sum of vectors that span W, namely the set of Wi's. But this can only be the case if AI is equal to BI is equal to 0 for every I and J. AI is equal to BJ equals 0 for all I and J, because we already showed that the WJ and VI are linearly independent. This means that the equivalence classes Vi plus W are linearly independent vectors in V quotient W. That is, now that we've shown that they span V quotient W and they're linearly independent in V quotient W, these vectors are thus a basis for this vector space. And we said the dimension of V quotient W is equal to n is equal to dim V minus dim W, since the dimension of V is m plus n and the dimension of W is m. And then you simply add the dimension of W to the other side, and you get the equality of interest. It then follows immediately that these vector spaces are finite dimensional, in the sense that, as we generate them, W only has m elements, m is finite, therefore W is finite dimensional, and we've shown that VW are spanned by n vectors, namely those of the form Vi plus W. Therefore, since n is finite, these are both finite dimensional. This concludes our proof about the sum of vectors and their sum of spaces and their subspaces, and the natural subspaces that arise from this. With that proof done, we can now consider a canonical basis for any vector space, namely a vector space f to the n, namely the set of all n tuplets of elements of the field, has a basis that can be described in terms of the Kronecker symbol, sometimes called the Kronecker delta, where you say delta ij is equal to 1 if I equals j, or 0 if I does not equal j. And use this to generate the Kronecker vector, or the Kronecker delta vector, which is delta j, which is simply delta 1j all the way up to delta nj, which is clearly an element of fn, because you're going to have 1 and 0 in your field, and therefore having a string of these is clearly an element in the set of all n tuples of elements of your field. We note that by the property of the Kronecker delta, this will be 1 in one entry and 0 in all other entries, in the sense that delta 1 is going to be 1, 0, 0, 0, 0. Delta 2 is going to be 0, 1, 0, 0, 0, all the way up to delta n, which is going to be 0, 0, 0, all the way up to 1. That is, all the coordinates are 0 except for the jth coordinate, which is a 1. And you see that the n vectors are linearly independent and span the vector space Fn. That is, choose any element in Fn. You can express it in terms of each of these by namely scaling the ith Kronecker delta vector to the ith entry, and adding those to all the other entries scaled by the appropriate index. Next, you note they're linearly independent because you can simply add them, and it's easy to see that the only way for them to equal the 0 vector is by having all 0 coefficients. Therefore, we can tell that the dimension of this is n, but we kind of knew that since these are n tuples. But these are more useful by noting that this is a very natural way of writing any vector, because you can use this basis to write any vector v as the sum from 1 to n of xj delta j, where these are simply the sum of vectors where they have the ith entry, the jth entry of v as the jth entry in this sum, and whose value at the jth position is exactly the same as this one. This also kind of gives natural coordinates in the idea that if you list out all of the v's, each of the elements of the v vector as numbers, you'll see that those numbers are exactly the coefficients on each of the j delta vectors. So you can think about these as a natural coordinate system for the space. We're calling that the coordinates are the coefficients on any basis. With that, we're wrapped up. We'll consider the very important topic of linear transformations next time. Thank you for watching.